Hello, welcome to our presentation on incentive-compatible role-based reward distribution in Algorand. This is a joint work by our team from Isfahan University of Technology, Florida International University, and University of Texas at San Antonio. In Bitcoin or other traditional blockchains, the consensus is achieved by the network selecting a leader in an unbiased fashion once every 10 minutes on an average, called round. The selected leader gets the right to commit or append a new block onto the blockchain. The network then implicitly accepts this block by adding on top of it or reject it by appending on some other block. That is the forking problem. These blockchains use proof-of-work mechanism to select the leader in each round, where miners compete with each other by solving a hash puzzle. This proof-of-work-based consensus mechanism, however, has several shortcomings. First, the hash puzzle-based proof-of-work approach is wasteful in terms of energy. Now the Bitcoin network uses more than 500 terawatt-hours of electrical energy that is comparable to Greece. Second, the traditional blockchains do not prevent forking and results in the uncertainty of transactions. Third, Bitcoin miners turning into pool mining to maximize their profits, and this can result in centralization. Today 3 or 4 mining pools have more than 50% of the hash power in the Bitcoin network. Finally, the traditional blockchains do not scale well with the number of transactions and network users. In comparison to the Visa payment network with more than 56,000 of transactions per second, the Bitcoin network can only process 7 transactions in a second, which is very low. Several solutions have been proposed to solve the traditional blockchain shortcomings. Of all these improvements, the Algorand protocol has garnered the most attention within the permissionless blockchain community, primarily because of its innovative proof-of-stake-based Byzantine consensus protocol that is not only energy efficient, but also provides strong security guarantees against forking in a network comprising of faulty and malicious nodes. Algorand eliminates the possibility of hash power centralization by removing the difference between normal network users and scales pretty well. In fact, Algorand can commit about 750 megabytes of transactions per hour, which is 125 times of Bitcoin's throughput. But, one critical issue has not received much attention, if any, is the protocol incentive compatibility. Before that, we need to explain the Algorand protocol. In each round of this protocol, the Algorand nodes randomly compute their roles as a leader, committee member, or other online nodes, to propose, vote for, and gossip the Algorand blocks and its transactions. To determine his role, any Algorand node employs a random role computation algorithm which is called the sortition algorithm. The sortition algorithm is implemented using verifiable random functions, which allow users to produce verifiable proofs using their private keys that can be publicly verified by the corresponding public key. Hence, the corresponding role for each Algorand node is not revealed until he sends it inside the header of a protocol-related message. The Algorand protocol can choose up to 70 leaders. The leader nodes should create their proposal for block out of their received transactions. At the time T1, each leader sends his proposed block to all first hop neighbors. Consequently, all nodes forward their received blocks to their neighbors in T2 and T3. After receiving block proposals, committee members try to reach consensus on 2 phases, that are reduction and binary BA* phases. These 2 phases at most take 13 steps with different committee members to avoid adversary attacks. Finally, at the end of each round, the Algorand nodes reach consensus on a single final or tentative block, or an empty block in the case of no consensus. The Algorand protocol guarantees the negligible probability of forking, let's say 10 to the power of -9, even in the case of Byzantine environment. But, similar to any other permissionless blockchain protocol, Algorand must also provide enough incentives to foster cooperation among its participants, whether they are leaders, committee members, or online nodes, to enable effective consensus. Let's assume that an Algorand node is cooperative when it plays its role, that means performing all the assigned tasks, and consequently, accepting all the associated costs. In contrast, a defecting node only remains online but does not perform any of its assigned tasks, except sortition computation to join the network. In this paper, we assume that all network nodes behave in an honest but selfish manner. The malicious node's behavior has been addressed in the main Algorand paper. Hence, in our work, nodes make a strategic decision to cooperate or defect solely by maximizing their own interests and incentives. To get an insight into the robustness of the proposed Algorand reward sharing approach against selfish node behavior, we conduct preliminary simulation experiments. Our simulator, written in Python, is based on the Algorand discrete event simulator by Deca and other, and implements all Algorand protocol modules, including sortition, reduction, and binary BA*. We are also able to simulate network delays, customize different network parameters, and reward sharing protocols. In each simulation instance, we randomly select defecting nodes, that are honest and selfish nodes who chose to defect given their payoff, using a uniform distribution. We consider the total number of defecting nodes in the network in steps of 5% to 30% of all the nodes in the Algorand network. The corresponding percentage of nodes who extracted final, tentative, or no blocks from the network messages are plotted in this figure. For example, as shown on the left side, with a 15% defection rate, most of the nodes do not reach any consensus on a final block after round number 30. Also, the results show that even with 25% defection the network fails in the first few rounds. That means no final block can be extracted after round 15. Hence, this simulation results show that without an incentive-compatible reward-sharing approach that fosters cooperation, rational nodes will be inclined to defect from the block creation and consensus process, resulting in failing to add new blocks. Recently, the Algorand Foundation has suggested a tentative version of their reward sharing. The proposed mechanism assumes the creation and maintenance of two reward pools, Foundation Reward Pool, and Transaction Reward Pool. These pools are nothing but public keys controlled by the Foundation. These public keys act as a central, Foundation-controlled, storage where reward distribution-related funds are deposited. All rewards for each round of the Algorand protocol are expected to be transferred from this public key. To bootstrap the new cryptocurrency, the Algorand Foundation implemented a ceiling of 1.75 billion algos, that is the Algorand unit of the Algorand cryptocurrency, to be dispersed from the Foundation reward pool in 12 periods as shown in this table. Each reward period spans 500,000 of block. But the transaction fees accumulated from the transactions in the added blocks during the bootstrap phase are saved or deposited into the transaction fee pool. This pool is not planned to be used for reward disbursement until the 1.75 billion algo ceiling of the Foundation reward pool is met. In the Algorand network, rewards are shared among nodes in proportion to their respective stakes, but without considering their roles. This means there is no difference between a leader, committee member, or the other online nodes in their received share of rewards except their stakes. We first try to analyze Algorand Foundation's proposed reward sharing mechanism. We proved formally that we cannot enforce cooperation in the current reward sharing approach for Algorand. If all users are rational, they will try to only play defecting and the system remains in all defection Nash equilibrium. Intuitively, this occurs because different nodes receive the same portion of the rewards despite bearing different costs depending on their role in the round. To overcome this, we propose a novel incentive-compatible reward sharing mechanism that shares rewards by considering node roles. As shown in this figure, we propose that the reward BI must be divided into 3 parts, and then be distributed among the nodes given their stakes. In our model, we assume that alpha, beta, and gamma are the proportion of the rewards which must be distributed among leaders, committee members, and other online nodes. These coefficients should be chosen by the designer, such that Algorand Foundation can enforce cooperation among users by considering corresponding costs. By considering this model, we have established conditions under which there is a cooperative Nash equilibrium. We have established a cooperative Nash equilibrium in which all leaders and committee members cooperate and the minimum number of other nodes that are needed to have a stable network also cooperate. But to reach this Nash equilibrium, the Algorand Foundation should compute the minimum BI value, that is the reward value which should be dispersed in this round, and the alpha, beta, and gamma coefficients. The BI value also depends on the minimum and the summation of stakes of leaders, committee members, and online nodes that have been shown by small and capital S annotated by roles, respectively. Next, we extend the current Algorand reward sharing method by considering the strategic behavior of nodes. In this case, we provide a solution for Algorand Foundation to foster cooperative behavior among all Algorand nodes using the bounds calculated by BI. This algorithm proceeds as follows: at the end of each Algorand round, the Algorand Foundation extracts the list of the leaders, the committee members, and other online nodes as L, M, and K. These values can be simply computed by processing and verifying the list of all the sortition proofs that have been sent by the Algorand nodes in their votes, as committee members, or in the header of their block proposals, as leaders. Also, the Algorand Foundation determines the set of other online nodes from their gossip network messages. Then, the Foundation will calculate the optimal values for alpha and beta to minimize BI, by using the defined bounds. Next, Algorand Foundation computes the rewards for each user based on alpha, beta, bi values, and its own stake. Finally, the foundation creates reward transactions for each node and gossip it to the Algorand network. In order to evaluate our proposed mechanism, we first conduct a series of numerical analysis to obtain the best reward shares in our model that are alpha, beta, and gamma values. We then simulate an Algorand network containing 500,000 nodes, in which the number of stakes for leaders and committee members is SL equals 26 and SM equals 13,000, respectively. We run simulations with 3 different settings, where we distribute 50 million algos among these 500,000 nodes using one uniform distribution and 2 different normal distributions. In each round, we also randomly choose 1,000 nodes, in which nodes with higher stakes would be selected more often. Then we generate a series of random transactions for the selected nodes with a uniform distribution. Hence, our simulation result in this figure shows the accumulative calculated reward in each round with our proposed algorithm and Algorand Foundation mechanism. This result shows that our proposed mechanism distributes much smaller rewards among nodes, given the distribution of stakes. For example, in contrast to the reward-sharing approach proposed by the Algorand Foundation, which shares 20 algos in each round for the first 500,000 rounds, our proposed reward-sharing algorithm will share about 5.2 algos for a normal distribution of stakes. More interestingly, our proposed solution will not increase the reward until 6 million blocks are generated, as it can guarantee cooperation without paying more algos. Our approach only distributes more rewards when the distribution of stakes obey the uniform distribution. This is due to the fact that the number of nodes with small values of stakes is higher with this distribution. As it is presented in our paper, if we can remove the nodes with smaller stakes, we can still keep the connectivity of the network and distribute much smaller rewards. Interested readers are referred to section V of our paper. In this paper, we first introduced a system model to capture the main operational features of the Algorand. We then comprehensively studied the problem of node selfishness in Algorand and proposed a possible solution to overcome it by employing game theoretic modeling and analysis. Our analytical results show that we can always enforce cooperation by carefully distributing the correct amount of rewards. Moreover, our numerical analysis validated that the proposed reward-sharing mechanism outperforms the current proposal by the Algorand Foundation. We believe that this work is the first step towards a better understanding of the effects of selfish behavior in Algorand. Our mechanism can help the Algorand Foundation use the algos wisely, as well as adapt dynamically with the distribution of stakes in the network. In terms of future work, we can also get in touch with the Algorand Foundation to introduce our proposed mechanism for reward sharing in the initial phase, for 1.75 billion algos, as well as the distribution of transaction fees as rewards in near the future.